Hi guys, so my name's Courtney and I'm here with Danica, and today we're going to talk to you about what we did for our Engineering 330 paper. So first thing at the top of the screen, you can see that Danica and I were both present for all but one of our meetings. And now for a little bit of an overview about our paper. First, we decided that we were going to go with a multiple vehicle traveling salesman problem using a random search algorithm. We did a literature review and we found a bunch of different articles, but the two main ones we used are listed here. And we decided that through the literature review that we wanted to try utilizing the k-means that Sergio used in his paper. And we also needed to adjust our cost function, which was given to us in our instructions, to add a fixed cost for our trucks, as well as adding a cost per mile traveled. All right, so this slide is basically just showing our pseudocode that we used. Our main goal is to find the minimized cost function, which, as we said in the previous slide, was we have a fixed amount for each truck and the cost per distance. So we're trying to find where these 2 points intersect. So going from the top, basically we're going to run the TSP once with only one truck. Then we're going to run it again where the number of trucks equals the total population. So each stop gets a truck basically. Then we're going to calculate cost and declare the best of the two. We're going to add and subtract 10 trucks to the best. We're going to go like above it and below it. And then we're going to run the TSP again with k-means to find the centroids and calculate the total cost. Then we're going to compare this total cost for both populations, the best and the current. And we're going to continue this tournament until we're no longer able to go up and down by 10. Then we're going to incrementally decrease. So we'll go up and down by 5, then up and down by 2, then up and down by 1, until the best one is found, and then our program is complete.
So getting into our code, we couldn't show you the entire code. There's like 300 lines in MATLAB, so it would take us forever to show you everything. But this code is the most important chunk out of MATLAB. It's what makes our algorithm or code kind of unique. So first of all, that top line dealing with the array, we created an array that would keep track of all of the different numbers of trucks that we had tried so that we wouldn't go back and retest something we've already tested. Then the main section of the code is while the increment is greater than 0, we do all these things. As Courtney had said previously, in our pseudocode, we start with an increment of 10 and then we divide that by 2, rounding down to the lowest number. So we start with 10, then we go to 5, 2, 1, and then it'll finally reach 0. So we add or subtract the increment from the current truck amount. So when we run it in the beginning, we start with one truck, or we have the same number of trucks as there are cities. If the one truck wins, then we would add the increment, but if the same number of trucks as we have cities wins, then we would end up subtracting the increment. We have error checking in there to make sure that the trucks doesn't go below 0 and it doesn't go above the current amount of cities. And then we use k-means, that's the next line, to assign the appropriate cities to each truck. K-means has to have an input of how many trucks you need, but then it outputs the centroids. So the big for loop in the middle here is actually going through and assigning each city to the correct truck. So we say that for O equals 1 to the current amount of trucks, nested in there for B equals 1 to the number of cities. If the index in the k-means index array equals the current truck that we're on, then you should include that city to that truck's route. So once the route for the specific truck is complete, we run the TSP for that specific truck, go through and run it again for every single truck in this loop. And each time it goes through each truck, it adds to that total distance where we can finally calculate the total cost and compare that cost to the best cost. And it goes over and over and over, looping through until our increment reaches 0 and we have found a best solution. Since not everyone is super familiar with coding, we decided to have an example problem. This might help the end user understand a little bit better what we're doing. So if we assigned the number of cities to be 50 and our truck cost, let's say, was $5,000 and the distance was $50 per mile, let's say, our code would start testing with just one truck. We would do the TSP for one truck. It would calculate the cost for that. And then since there's 50 cities, we would assign 50 trucks, one truck per city, and do the total cost for that. In this case, having one truck per city, so a total of 50 trucks, is better than having just the one truck. So because of that, we're going to increment down by 10 to 40 trucks. And we run the TSP for each 40 trucks in that loop and find the total cost for that, and it ends up being better than the 50 trucks. So 40 is our current best, and then it's going to increment up and down by 5. So it'll go to 45, then 35, then it'll increment by 2, so 40 is still our best, so it'll go up to 42, try 38. 42 is our best, so it'll go up and down by 1 to 44 and 43 and then 41, and it lands on the correct answer being 42 trucks with a cost of $237,100. Our code takes about less than 200 seconds to run, but it also depends on each problem. This answer here with 42 trucks and that total cost is it's for that specific problem. Each time that this problem is run, the cities are randomly generated. So the answer is going to be around 42 trucks each time, but it can differ. So here you can see our actual MATLAB code. Since we've already run through an example problem and talked through our pseudocode, I'm not going to talk through this code, but I will scroll down through it. So if you want to see anything, you can pause the video as I'm scrolling through to continue reading. But this is our code, running the original TSP, going through the genetic algorithm. Here we calculate the number of trucks as there are cities. We do the while increment loop with all these lovely if statements to go up and down. We run the TSP again for each individual truck, and still TSP, and then it calculates the best and compares the best and finally outputs the final best. So when we ran this problem, I'm not going to run it just because it takes like 200 seconds, but we previously ran it, and I'll scroll through this so you can kind of see. It starts with that current truckload of 40 trucks, goes through each city, calculating the TSP. So you see it went from 40 down to a current truck of 30. Go down. Now we're at 45. Get to 47. Goes down to 43. Goes up to 46. And ends with 44 with our best cost of $232,980. This is our last slide for the presentation. It's just kind of a comparison slide and conclusions. The unique features of our code is that we're using a very, you could say, basic version of regression to find the number of trucks. One way you could have done this is to loop through every single amount of trucks from 1 to 50 or 1 to the number of cities, but ours doesn't have to do that because we're using that variable incremental change. Another unique feature is that we're using k-means algorithm to assign the cities to the trucks. A lot of different TSP algorithms out there will use a random search with breakpoints, and it will just randomly reassign these over and over to hopefully get a better solution. K-means is a little bit more of a stable assignment of those cities to the trucks. Overall, we have a really accurate solution, but it's kind of slow sometimes. Sometimes it runs as quickly as like 50 seconds, but more often than not, it's closer to 200 seconds, and this is much slower than some other algorithms that exist out there. But ours does allow for an unknown amount of trucks instead of having to assign a certain amount of trucks up front, like some of the other k-means algorithms we see. So in conclusion, Courtney and I have spent the last 3 weeks or so, I guess, compiling this code, PowerPoint, and paper. So we hope that was helpful. And yeah,
Thank
330
you.
paper. Thanks, guys.